Now, please welcome Dr. Nick Ashworth from the Defense Digital Service.
Hello, everybody. Can you all hear me okay? I will apologize. I don't have any slides for this. I figured a live demo would be a little bit better. So I'm Dr. Nick Ashworth. I'm from the Defense Digital Service. We are a part of CDAO, the Chief Digital and AI Office, which works under the Secretary of Defense. So we're an OSD organization. And this here is Combi. And assuming he wants to play nice right now, hey, Combi, go ahead and introduce yourself to everyone.
Hello, everyone. My name is Combi, and I am a robot designed to showcase how AI can interact with physical systems in a secure way. I'm excited to be here at the Robotics Expo and to meet all of you. If you have any questions or just want to chat, feel free to ask.
So yeah, in case you couldn't guess, my research is tangentially related to robots. What I do and what I've been focusing on for the past year or so is using generative AI models to interface and control and read from physical systems and sensors. Combi here is the test bench for this. So he's the friendly, did not volunteer for this, but he's here anyway, experimental platform that we've been working on. One of the reasons why so I guess to take a phrase back, you've had a lot of talks from the DoD today of different sectors, of all of our work of using AI models at large for very specific military systems, for future systems, everything. My research area has focused on existing physical systems, so think things like radar, electronic warfare systems, stuff like that. Because one of the avenues that I think generative AI in general provides a very unique solution in this space is the concept of like, how do I reduce the amount of training an operator needs to use specific systems, and how do I simplify the use case process so that you don't have to spend every workday staring at a terminal window. There are plenty of reasons to join the DoD. We are in desperate need of people to actually join the DoD, for those of you who've been paying attention to the news. No one who joins the DoD wants to be like, I'm going to be a radar operator, and I'm going to sit in a shed and stare at a screen and maybe call a radio whenever something, like, you want to do more. You want to do more with people. And the nice thing about where generative AI models are at now is that we can finally do that to where you can kind of just bolt on intelligence. Now, whenever you do that, some funny things happen. So if you know traditional control theory, the rules of control theory are your controller must be deterministic and it must be discrete. This is true if it's a keyboard, if it's a joystick, if it's a gamepad. And the reason for that is your controller is supposed to be custom to the system you're controlling, not the user. Language is dynamic. Language is non-deterministic. We create new words all the time. Words change meaning and phrases. It's all kind of crazy. And so whenever you switch to using a non-deterministic and a dynamic controller and break control theory, a very funny thing happens because the rule flips. Your controller is no longer custom to the object you're controlling. Your controller becomes custom to the user. This ends up becoming very exciting in this space because it means that you can now talk to and communicate with systems in plain text. And so, for example, I can do something like, say, Combi, turn left 90 degrees, and give a very specific request, and he does his best to follow that out. The carpet's been messing with his wheels all day, so I apologize for the accuracy. Or I can do something very broad and generic, like, hey, Combi, do a funny dance for the people. And we will hope he doesn't fall off the stage.
I may not have legs to dance, but I can do a little wiggle. Watch this.
Nope.
What do you think? Was that funny?
I promise he's okay. He has a family, I swear. But anyway, what you saw there was basically adding non-determinism to a normally deterministic system. The way we're working behind the scenes in the code, so like if we pull back to go into the kind of the framework thing, we're doing a couple weird things compared to some of the other stuff you've seen here. We're not using any kind of custom trained model or anything. This is purely foundational models as they are. Right now, for speed's sake, we're using OpenAI 4.0 Mini, just because it's faster and it's running on Raspberry Pi. If you look at our code up on GitHub, we show you running on Llama and running on Mixtral. It all works the same because we're purely doing context manipulation. It's just a lot slower. So for demo's sake, that's why we're doing it on this. One of the big reasons why we're wanting to do it in like a context-focused way, as opposed to going to some of the other stuff you've seen here, where people have proposed making custom models for this, or doing multimodal operation where they just have one AI model that does everything. My background is a hacker. I hack airplanes for a living, which is a very fancy way of saying I've made my entire career of exploiting someone else who said, you know, I'll fix that eventually, and then I come along. And for those of you who aren't familiar with cybersecurity, it's a pretty well-opened treadmill. There's constant bugs and vulnerabilities in code. And even on the stuff that's super easy to patch, like Windows updates and stuff like that, we can't get people to do it. And this is including things where like Microsoft does everything but punch their fist through the screen and push the reset button for you. Now, it's true, we're not at the point yet where we are regularly finding vulnerabilities in models. We're actually not even the part yet where what a vulnerability in a generative AI model means is even commonly agreed upon. However, we will get there eventually. And when we get there, the problem then arises, if I, the hacker, report that there is a problem in your model, fixing it is no longer just pushing a button accepting the Microsoft update. Fixing it means having to go through retraining, which is expensive and time-consuming. And as we've already seen with a couple of the companies that have already released hardware, think like RabbitR1 and some of those other guys, the moment you're asked or required to retrain your model, it becomes incredibly expensive and very hard and difficult as a company. That becomes even more true even if you're the government. Because spoiler alert, we have more airplanes than everyone else in the world, and they're all different. And so if we go down making a bespoke model for every one, we will never fix anything. And so that's kind of where this research has been going on. The source code and everything is all public. The build is for under $1,000. I apologize, he's not Spot the robot, but that's harder to afford on personal budgets. But yeah, everything's open source. It's on our GitHub if you want to mess and view them. We'll also be around if you want to play with it. I just thank you, SASP, for giving us the opportunity to present here. This is like a very kind of fun, cool part of the research that I think gets kind of ignored a lot. It's easy to focus on the big flashing stuff of doing like, well, what if we do a full vertical pipe system? What if we make everything that? There's a lot of cool stuff on AI, and whether it be robotics or whether it be physical systems at large, that's going to be changing the next 2 years. And I think it's going to be really exciting. It's really going to change how, like, both what we consider interacting with a system to be and how we do that in the future. So I think I got like a minute left, so I will try to be nice and give back time early. Thank you all. I hope you've had a wonderful conference. Feel free to swing by in the after hours. Thank you all so much.
Finally, please welcome Sviat Dulyaninov from Bright Machines.
All right, can you hear me? Good. I know I'm the last person before the drinks and the reception, so I really appreciate your patience, and I'll try to keep you entertained. Just 2 slides and then a lot of videos of the demo. I'll spend 1 minute on the company and 1 minute on our product buckets, and then 4 different demos that you're going to enjoy, I hope. So the first thing I want to say, Bright Machines, we're 6 years old, recently raised Series C. We focus and were created on the thesis of reshoring and strengthening manufacturing in the United States. What we do, we build robotic systems powered by machine learning and AI that are flexible enough to build different electronics and upskill humans and build lines within the United States to build high-value electronics. We already have more than 110 microfactories, that's how we call our lines, deployed around the world, but mostly in the United States, but also in Europe and Asia. We focus on the segment of what we call AI backbone or AI hardware, everything that goes into the data center, like a server, network equipment, data storage, or even energy storage. We are around 180 people with headquarters in San Francisco, and here you can see a few recognitions from Forbes to Fast Company and Inc., and so on and so forth. Speaking about our product buckets, you can see 5 on this slide. The first one is what we call design for automated assembly. That's what we are building this year. We are doing it with close partnership with NVIDIA Omniverse. This is a plugin to recommend engineers how to create better designs so that they are easier to automate and produced at higher quality. The second thing that you can see is Bright Machines Microfactory. That's our robotic lines. We have different types, enclosed and open, but that's the hardware piece. Then you have Studio, this is a development environment, how you introduce new products to the lines. Then Platform, what runs automation and collects data. And then finally, you can use that data for insights and building applications on top of it. And now, I'll go through the demo part. So the first video you're going to see is about what we call smart skills. Smart skills is the brain behind automation. This is machine learning. This is how we navigate and inspect and how robot makes a decision what to do. So here you're going to see how we create a 3D model of a new product that arrives at our lines. This is an example of a server that goes to the data center. This, what you see, is like the 3D model we create within around 4 hours, usually. And after we create this model and create what we call a recipe, the flow of assembly, you can see that the robot can start just putting memory modules, DIMMs into the slots. It's not going to put all the way because it's a demo, because you destroy the socket, but the idea is it does it instantly. The other thing, you can see the 3D capabilities. So we change the angle to like 15 degrees or so, and within a second, robot navigates and can still place the memory module to the socket that it needs to put it to. More than that, if you even do the double stacking, it's not going to overthink it. It's going to also take a second and do the same. It doesn't really happen in a production environment, but it just shows the level of flexibility. Because when you think about modern manufacturing, everybody who uses automation, they use fixtures and gigs, and like everything is fixed. This is another example of smart skills in case for inspection. This is debris detection, so we're just going to run inspection. This is like how a Brightware platform looks like. And you're going to see the debris in the areas of interest. The areas of interest in this case are the sockets for the memory modules, and you can see debris there. First of all, you wouldn't believe, but it happens. Like in manual assembly, people leave screws in the servers. And second of all, we can even see a hair, so we're going to avoid putting DIMM on it. This is another example of inspection. This is the second pipeline that we call, for putting in different buckets and classification. This is going to classify DIMMs into two things. One is open and the other is closed. And you can see that closed are in green and open are in red. And then that's how we can navigate the robot where to put them. And finally, the big difference versus any automation is the changeover time. Our changeover time is like 0 to 1 second if we know what server type we have. This is an example of navigating to the server that is smaller, easier to assemble on the left. Then we're going to choose another server and just going to move it into the area that the camera can see. And within, so you see, like it takes a second, it's going to think a little bit, and then it can instantly put the memory modules into a new type of server, which is also unheard of because when you do the changeover in modern facilities, even if they're like top-notch and you use automation, it's going to be hours usually. That's on smart skills. The next demonstration I will show, this is our facility in San Francisco, a new office we moved to recently. This is another example of our microfactory. You can see cobots that was covered like a few hours ago on one of the panels, collaborative robots, 2 stations. One is going to do pick and place of a GPU, and the other going to do like 17 screwing operations to put this GPU into the server chassis. The GPU itself, the GPU module from NVIDIA, it weighs around 100 pounds. So right now, if you look at any assembly of those GPU modules to modern servers, it's going to be 2 people and a crane to move that. Like, think about this, an item that costs $250,000 being assembled by 2 people and a crane, and like the price of mistake is pretty high. So we do it with the same software. You can see the cameras on the canopy above the robot. So using the same smart skills, we take GPU module and place it in the server chassis. And again, you can see nothing is fixed. This is just a trolley, so you can move it. And if you moved it before the action, the robot is going to find the proper place and put it there. And you need to be really precise because it can damage the board. The second operation you're going to see in this video is going to be putting 17 screws to connect the GPU cluster board H100 to the server chassis. And it's going to be the second cobot with a different end of arm, which is going to be a screwdriver. And now you're going to see how those screws are going to be connected. So you can see the screwdriver, 17 screws, really hard to get into because they're like between GPUs, around GPUs, and you need to find it through vision and be really precise with your torque and pressure. So we measure all the data to be really consistent and don't break the board or any equipment. Overall, this whole system that you see on the screen right now, is around $300,000. So you can imagine kind of a Ferrari being assembled on this line. Because this is like pretty hard to get for a human also, because like, you know, and for the camera because of the shade and other things, but we can still get it. And more than that, this is zero scrap operation. So we guarantee that like none of the items that goes through this process would be damaged in any way. Then quickly to what I mentioned, what we call design for automated assembly. Again, this is a plugin, as I mentioned. We work with any CAD solution like Autodesk or Siemens or others through NVIDIA Omniverse. We simulate and then give recommendations. And just a quick video of like how, this is like a quick demo, how you do the server design as an engineer. For instance, you think about where to place CPUs, memory modules, heat sinks. Our system going to simulate it. You can see the similar box that you saw before with the Fanuc robotic hand, and it's going to take and simulate how you're going to assemble this server. And after this, you're going to receive as an engineer report with some insights and advice how to make it a better design. So again, we focus on DIMM memory module insertion applications just to make it easier and to follow the same flow of the demo. And then finally, I want to finish with one last video of how we assemble energy storage units. And this is going to be before and after. And before is how our customer assembled energy storage units that go to data centers, hospitals, schools for backup energy in one of the Asian countries. And after is how we do that with our robotics and AI in the state of New York. So enjoy. I hope it's going to be really educative. There's a number of steps. You can see a human on the left. This is battery insertion into slot modules. You can see the difference in speed. This is our robotic cell that made it really fast and high quality, really consistent. The next step is like rib module insertion. Also, you can see the difference of like manual versus automated within our next cell in the process. Then there's another cell that goes through the conveyor. It's cell module insertion. Also, you can see the difference. Similar logic. And then finally, this is like battery bus bar placement, another thing, which is also like precision is very different and accuracy is different. So I will stop there. I have 7 seconds left, so it's perfect timing. Thank you very much for your attention. Thanks for organization of the event, and enjoy the reception.